Welcome to Chapter 9, Estimating the Value of a Parameter. Section 9.2, Estimating the Population Mean. Okay. Objective 1, obtain a point estimate for the population mean. So remember, the goal of statistical inference is to use information obtained from a sample and generalize the results to the population being studied. As with estimating the population proportion that we did in section 9.1, the first step is to obtain a point estimate of the parameter. The point estimate of the population mean, mu, is the sample mean, x bar. So the best single guess for the population mean is the sample mean. So in our first practice here, the following data represents the amount spent on Valentine's Day among males who purchase gifts for the holiday. The data is based on reports from fundevo.com. Okay, so here are all of our data values. We are asked to obtain a point estimate of the population mean amount spent on Valentine's Day among the males who purchase gifts for the holiday. Okay. So what we would do is we would take this data and we would enter it into our calculator, and we would need to find our point estimate. And remember, the point estimate for the population mean is the sample mean, which means we would need to find X bar. Okay. So let's do that. Alrighty. So let's go to our list and let's enter in our data. 216, 156, 125, 133, 229, 155, 146, 120, 189, 201, 137, and 262. Alrighty. Let's make sure that I have all the numbers there correctly. 146, 155, 229, 133, 125, 156, and 216. Awesome. All right. So to get our sample mean, we are now going to need to go to stat, tests, and then we're going to need to go to calculate, one var stat. So press enter. Our data is in list 1. So then we're going to go to calculate, and we're going to look at X bar right here. So 172.41666667. Okay. So our sample mean is going to be 172.42. So that means the point estimate for mu is $172.42. Objective 2, state properties of students' T distribution. So suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution below follows the student's T distribution with n-1 degrees of freedom, where X bar is the sample mean and S is the sample standard deviation. Okay, so this is our formula for T with n-1 degrees of freedom. Okay, so now why are we using T instead of Z? Didn't we use Z-score for normal distribution? Why are we using T? Well, when we don't know the population standard deviation sigma and must estimate it, using the sample standard deviation S, we introduce an additional uncertainty. So the t distribution accounts for this extra uncertainty. All right, so that's why we use t instead of z. So you can kind of think of it as the t-score. So let's now understand a little bit about the degrees of freedom. Okay, so n minus 1 degrees of freedom, because the first n minus 1 observations have freedom to be whatever value they wish, but the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to equal 0. Okay, so just think of it this way. Like if I were to tell you that the mean of 3 numbers is 10, and I tell you 2 of the numbers are 8 and 9, you can figure out the third number, and that third number must be 13, because 8 plus 9 plus 13 equals 30, and 30 divided by 3 equals 10. So that third number, 13, has no freedom. It's locked in by the other values and the mean. A visual understanding of the t distribution is that the histogram for t is symmetric and bell-shaped, with the center of the distribution at 0, but the distribution of the t has longer tails, which means t is more dispersed. So it's unlikely that t follows a standard normal distribution. The additional spread in the distribution of t can be attributed to the fact that we use S to find t instead of sigma. So because the sample standard deviation is itself a random variable rather than a constant such as sigma, we have more dispersion in the distribution of t. So let's now walk through the properties of this t distribution. The first one, the shape of the distribution is different for different sample sizes. So that means smaller samples have fattier tails, or they're more spread out. So as the sample size increases, it looks more like the normal distribution. The second, the distribution is centered at 0, so it has a mean of 0 and is symmetric about 0. So this is just like the standard normal distribution. The third property is that the area under the curve is 1, and the area under the curve to the right of 0 is going to equal the area under the curve to the left of 0, which is a half. So the total probability is 1 and split equally on both sides of the mean. Okay, the fourth property, as t increases or decreases without bound, the graph approaches but never equals 0. So that means the tails extend forever, just like in the normal distribution. Property 5, the distribution has standard deviation greater than 1, which means more variation. The area in the tails of the t distribution is a little greater than the area in the tails of the standard normal distribution because we are using S as an estimate of sigma, therefore introducing further variability into the t statistic. So more uncertainty means wider distribution. And property 6, as the sample size n gets larger, the t distribution gets closer to the standard normal distribution. This result occurs because as the sample size n increases, the values of S get closer to the values of sigma by the law of large numbers. So for large samples where n is greater than or equal to 30, t and z are very similar. So when to use the t distribution? We use the t distribution when sigma is unknown and either n is greater than 30 or the population is normally distributed. So we use the standard normal distribution when sigma is known. And that's not covered in this course, so we don't have to worry about that process. Okay, so the key decision rule here, to conclude all these properties is that when the population is normally distributed or n is greater than or equal to 30, we use the t-distribution. When it's small, when n is less than 30 and the population is not normally distribution, the methods don't apply. Okay. All right. Objective 3, determine t-values. So let's first understand t-values and critical values. So the notation z sub alpha is a z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. So similarly, t sub alpha will be the t-value such that the area under the t-distribution to the right of t sub alpha would be alpha. So what does this mean? So just like when we found z-scores for the normal distribution, we can find t-values for the t-distribution. The subscript, so this alpha, tells you, let me get my pointer. This alpha tells you what area is in the tail. All right. So the shape of the t-distribution depends on the sample size n. Therefore, the value of t sub alpha depends not only on alpha, but also the degrees of freedom n minus 1. So the table in the back of your book in Appendix A, it's also in your formula chart, as you see here, has the degrees of freedom on the far left-hand column, and the top row represents the area under the t-distribution to the right of some t-value. So unlike the z table, which is the same for all problems, the t-distribution table changes based on your sample size, in other words, your degrees of freedom. Okay. So there are two ways that we can find our t-values. We can use the table or we can use our calculator. Obviously, the calculator is easier, but you can use either one. So let's do an example together. So we are going to find the t-value such that the area under the t-distribution to the right of the t-value is 0.05, assuming 20 degrees of freedom. That is, find t sub 0.05 with 20 degrees of freedom. So for our table, we are going to look at the degrees of freedom and our area. So we know t sub alpha, so we're trying to find that t value that gives us an area to the right of 0.05. So we're going to go into our formula chart. We're going to find our degrees of freedom, which is 20, and our alpha, which is 0.05, and the intersection gives us the number 1.725. Okay, so our t value is 1.725. So now we're going to use our calculator. And in our calculator, we are now going to use the inverse t. We've used inverse norm before, but in this case, we're going to use inverse t. Now for inverse t, our area here is going to be the area to the left. Okay, so that means we're going to be using 0.95 because we want the area to the left to be 0.95, which means the area to the right is 0.05 as the problem gave us. Okay, so in our calculator, all right, we are going to go second vars, and inverse t is now number 4. Okay, so let's go to number 4, enter. Our area is 0.95, and our degrees of freedom is 20. So we're going to paste that and press enter. In rounding to 3 decimal places, we get the same value that we got before, 1.725. Alrighty. Objective 4, construct and interpret a confidence interval for a population mean. Okay, so when to use this method? We need to consider these assumptions. The first one, So that sample data came from a simple random sample or randomized experiment. Second one, sample size is small relative to the population size. So our sample size is less than or equal to 5% of the population size. And three, the data came from a population that is normally distributed or the sample size is large. So we need random sampling, a small sample compared to the population, and either a normal population or a large sample size. Okay. Our confidence interval is going to be similar to what we've looked at before, where we have a lower bound and upper bound. Note here that X bar forms the basis of the interval for constructing and interpreting the population mean. So the margin of error is going to be subtracted from it and then added to it. Okay, as you see here, X bar plus or minus E. Okay, so just like with the proportions, we can take our point estimate X bar and add and subtract the margin of error to create a range. All right, so to construct a confidence interval for a population mean, we can utilize the calculator. In our calculator, we will go to stat and then over to tests. The test we are using is number 8, the T interval. And in this interval, we're either going to highlight either the data that we've entered into our calculator or stats if we know the statistics that were given to us. If data, we'll enter in the confidence level and calculate. If it's stats, we'll enter in our stats given to us and our confidence level and then calculate. Okay. So use data when you have the actual list of numbers and use stats when you are given summary statistics. So in this example, for a simple random sample of 42,007 Ford Mustang 6-cylinder 4-liter 5-speed manual, the mean gas mileage was 20 miles per gallon with a standard deviation of 1.5 miles per gallon. We need to verify the assumptions. And there are 3 assumptions we need to verify. The first one being is that the sample data came from a simple random sample. And it did, because I said it did. Simple random sample. The second assumption that we're going to make is that the sample size is small relative to the population. So that means N must be less than or equal to 5% of the population size. So we need the population to be at least, let's see, at least 800, because 400 is our sample, 40, not 400. 40 divided by 0.05 would get us 800. And then our third assumption is that the sample size is large. Well, N here equals 40, which is greater than 30, so we're good. So why does this all matter? Why do we need to verify assumptions? Well, we need to verify when we use the t distribution. So since n equals 40, which is greater than 30, we don't need to worry about whether the population is normally distributed or not. So for B, we're asked to construct and interpret a 95% confidence interval for the true mean gas mileage of the 2007 Ford Mustangs. So we are given X bar, which is 20, N, which is 40, S, which is 1.5, and our confidence level is 95%. So written as a decimal, it is 0.95. Okay. So now we can use the T interval on the calculator to find our confidence level. So let's do that. All right. So we are going to go to stats, over to test, and then T interval is number 8. So you can scroll all the way down to number 8, or you can just select number 8. And we have our summary statistics. So we're going to press enter. We have our X bar, which is 20. We have N, which is 40. We have S, which is 1.5. And we have our confidence level, which is 95%. All right, and we'll press calculate. So our confidence interval is 19.52 and 20.48. So now we need to interpret. So we are 95% confident that the true mean gas mileage of similar 2007 Ford Mustangs is between 19.52 miles per gallon and 20.48 miles per gallon. Okay. So for C, is it possible that the true mean gas mileage is greater than 23 miles per gallon? And is it likely? Well, yes, it is possible that the true mean gas mileage is greater than 23 miles per gallon. However, it is not likely. Now, why? Well, let's look at our confidence interval, right? Our confidence interval that we found was 19.52 to 20.48. And the true value, or sorry, not the true value, but the value here of 23 is not in this interval and is actually quite far above our upper bound of 20.48. So while we can never be 100% certain about population parameters, our interval suggests the true mean is most likely between 19.52 and 20.48, making 23 miles per gallon very unlikely. All right, next example. So the following data represents a simple random sample of ages of West Nile virus victims in the United States during 2007. Identify the outlier. We're just looking at this data right here. We can see that 25 is our outlier. Okay, so it's much younger than the rest of the ages in our data. Okay, it is, I guess you can say, significantly separated from the rest of the data, would be the more descriptive way of saying it. Okay, because most of our ages here are between 48 and 86. Majority of them are. Okay. So for B, we are now asked to construct a 99% confidence interval with the outlier included. Okay, so to do this, we are going to go into our calculator and enter in all of this data. So stat, edit. I'm going to enter all this data in my list 2. So 25, 48, 73, 65, 63, 81, 56, 86, 80, 77, 72, and 60. Okay, I want to make sure I have it all. 72, 77, 80, 86, 56, 163, 65, 73, 48, and 25. I do. Great. Then I want to go to the T interval. Okay. To get to the T interval, I'll press stats. Then I'll go over to tests and then to number 8. This time I'm going to select data. And I need to change my list to list 2. So second stat, select list 2. My confidence is 99, so that's 0.99, and then calculate. All right, and I get a confidence interval of 50.268, 80.732. All right, awesome. So next, it says to construct a 99% confidence interval with the outlier removed. Okay, so our outlier removed would be the 25. So let's go back to our data. And now we want to delete this 25. So I'm going to delete it. So now it's no longer there. And I'm going to go back to my T interval, which is number 8. Select data, Everything else stays the same. Calculate. And so now my interval is 57.933 and 80.43. Okay. So D is asking us now to comment on the effect that the outlier has on the confidence interval. Okay. Well, the outlier expands the confidence interval. Okay. So the outlier 25 increase the variability in the data, which increases the sample standard deviation S. So a larger S creates a larger margin of error, which makes the confidence interval wider. So when we had the outlier, our width was approximately, let's go back here, so 50 and 80, so approximately around 30 years, a little over 30 years. And then when the outlier was removed, we had, let's see here, maybe a little over 20 years. So the interval is about 10 years wider than when we included the outlier. Okay. All right. For our last example, I'd like for you to pause and attempt this problem, and then we'll walk through it together. Alrighty. So in this example, the following data represents the age in weeks at which babies first crawl based on a survey of 12 randomly selected mothers conducted by Essential Baby. So you would need to take all of this data and enter it into your calculator. You would need to make the following 3 assumptions before moving forward. One is that your sample data comes from a simple random sample. 2, your sample size is small relative to your population. So with 12 babies in the sample, the population must be at least 240 babies, because that would be 5% of that would be 12. And then the data comes from a population that is roughly normally distributed. So with a sample size where n equals 12, we must verify that the population is approximately normal. And we would check this by using the normal probability plot or, of course, a histogram. But since n equals 12, which is less than 30, we cannot rely on the central limit theorem, so we must verify that the data comes from a normally distributed population. Okay. B, you're asked to construct and interpret a 95% confidence interval for the population mean age at which a baby first crawls. So you would be using the T interval in your calculator. When you calculate that, you would get a confidence interval of 31.938 and 43.567. So we are 95% confident that the true mean age at which babies first crawl is between these 2 numbers in weeks. So what could be done to increase the accuracy of the interval without changing the level of confidence? Well, we could increase the sample size. Why does this work though? Larger sample size, remember, means smaller standard error. Smaller standard error means smaller margin of error. And if you have a smaller margin of error, you have a narrower or more accurate confidence interval. So more data is more precision without sacrificing the confidence interval. Okay. All right. So that concludes section 9.2.